In this video, we will talk about polar coordinates, an alternative way to put pairs of numbers in correspondence with points in a plane. To put this in context, let us think about the usual Cartesian coordinates. How do they work? Well, Cartesian coordinates are a way to map pair of numbers x and y to points in the plane. Okay, so how is this done? So say you're given pair of numbers x, y, and a system of Cartesian or rectangular coordinates. Then what you have to do is to start at the origin right here, move x units to the right, or left, depending on the sign of x. So if x is positive, you would move x units to the right. If it's negative, you would move absolute value of x units to the left, and the same for y in the vertical direction. So what you would do is, let's say x and y are positive for simplicity. You would walk distance x to the right horizontally, and then you would go distance y up. So say like this. So then the point with coordinates x, y would live right here. So this would be the point with coordinates x, y. And so the way to find it is to go x to the right and y upwards, where x and y denote the units measured in some fixed system of units. So you can use imperial units, you can use metric units, and so on. But this is a way to find a point in the plane given pair of numbers x, y. And vice versa, if you have a point in the plane somewhere, and system of coordinates with fixed units, then you measure distance from that point to the y-axis, and that gives you the value of x, the first coordinate. If you measure distance from this point to the x-axis, that gives you the value of the y-coordinate. And so in this way, you're implementing such a one-to-one correspondence between pairs of points, pairs of numbers, that is, and points in the plane. Now, this method, this algorithm that corresponds to Cartesian coordinates, just happens to be one that is convenient under some circumstances, but under other circumstances, it may happen that we are better off with a different way to take pairs of numbers to points in the plane and vice versa. So another way to start with a pair of numbers, which will denote r and theta, and go to a point in the plane and backwards, is as follows. So suppose you have a plane in which there is a fixed axis, like so. So this is similar to the Cartesian case, where we have to fix the origin and axes and direction of the axes, and also the units. So for polar coordinates, you fix the origin, which you call the pole, and the axis, and then you work your way like so. Suppose that r and theta are positive for simplicity. Then what you do is you measure the angle theta counterclockwise from the direction of your axis. So let's say this is the direction of your axis. Then you want to measure, to take this and effectively rotate it counterclockwise, say like this. So now you're looking at the angle here of size theta. Okay, and then you want to measure distance r along the ray that forms angle theta with the direction of your axis. So this is the fixed direction of the axis. You measure angle theta counterclockwise. So this is similar to how you would do it on the unit circle. You measure your positive angles counterclockwise and negative angles clockwise. So you start with the direction of the axis, measure the angle theta counterclockwise, draw a new ray in that direction, and then on that ray you go in the positive direction if r is positive. So say you end up over here. This distance is r, and this is the point with polar coordinates r theta. Okay, so once again, if you have a pair of numbers r theta, then what you have to do to arrive at a point in the plane that corresponds to this pair, assuming that you're working in polar coordinates, is the following. You measure the angle theta counterclockwise from the direction of your axis, and then if r is positive, you walk in the positive direction along the rotated version of your axis. So there would be this you rotate your axis counterclockwise. This is the rotated position, and then on the axis you still have the positive direction, which is that way, and the negative direction, which is that way. And so depending on the sign of r, you go either in the positive or in the negative direction. So let us look at some examples to illustrate this. So let's find the point with polar coordinates 1, 5 pi over 4. So the way to do it is, first you have to fix an axis and the position of the origin on it. Then you have to measure angle theta counterclockwise, since theta is positive, counterclockwise from the direction of the axis. And so we have to measure the angle 5 pi over 4, which is pi, the angle of size pi, plus the angle of size pi over 4. So it would be pointing somewhere in this direction. So we have our axis positioned like so, and the positive direction is now over here, right? As we take our axis and rotate it like so, counterclockwise, by the angle theta equals 5 pi over 4. This is where we end up with. And then, since r is positive, we have to walk distance r, we have to measure distance r along the axis. So say we end up over here. So if this is 1 unit of length, then this is the point with coordinates 1, 5 pi over 4. Another example. Let's find the point 2 minus 2 pi over 3 in polar coordinates. So we start with our axis. There's fixed origin on it, which we call the pole. And let us find the point that corresponds to these polar coordinates. So this is our theta, and this is our r. We have to measure the angle of size minus 2 pi over theta, starting from the direction of the axis. So since our theta is negative, we'll be measuring it clockwise in this direction. So we will need to form an angle of size 2 pi over 3 in the clockwise direction. So that would be somewhere here. So that will be the positive direction of the axis. So what we just did, we measured the angle theta. Since the angle is negative, we measured it in the clockwise direction. So this is the angle theta equal to minus 2 pi over 3. So we are measuring angles in exactly the same way as we would on the unit circle. And now r is positive 2, so we have to measure the distance 2 up to here along the positive direction of our axis. And so this, if this is of length 2, then this is the point 2 minus 2 pi over 3 in polar coordinates. So there are several remarks to do here. So if you have a point with coordinates r theta, by changing theta by a multiple of 2 pi, you'll get the same point. So any point with coordinates r theta is the same as the point with coordinates r theta plus 2 pi k, where k is any integer. So what this is saying, instead of going, say, by the angle minus 2 pi over 3, we could have formed an angle of size minus 2 pi over 3 minus 2 pi, and that would involve making another full turn in the clockwise direction, which means we would end up at exactly the same point over here. So every time you're adding a multiple of 2 pi to the polar angle theta, you're effectively making a full circle around the origin, which puts you at exactly the same position. Similarly, what you can do with r, you can always make r negative. So here, for example, instead of going 2 in the positive direction, we could have gone 2 in the negative direction over here. But that is the same as to say, let's keep r positive, but change theta by pi. So here I will be adding 2k plus 1 times pi to theta. So that's an odd integer. Here we had an even multiple of pi, and here I'm adding an odd multiple of pi to theta. So to illustrate that such points are in fact equal, let me take say this example here, right? So we have this point with coordinates 2 minus 2 pi over 3. So this property here claims that if I reverse the sign of the radius and add pi to the angle, will end up at exactly the same point. So here I have added pi to the angle and I have negated the radius. Let us check that the point with polar coordinates minus 2 pi minus 2 pi over 3 is at this same location. So the way to do it is to measure the angle of size. Right, so this would be minus 2 pi over 3 if you perform the subtraction. So what I want to do is I want to measure the angle of size pi over 3. In the counterclockwise direction, because it's a positive angle. So this here is the angle of size pi over 3. Notice that it means that my axis will end up pointing in the opposite direction compared to this here, because these are complementary angles. This is 2 pi over 3 and this is pi over 3. And so after I end up rotating my axis in this direction, now I have the positive direction on the axis pointing here. So if I want to go to minus 2, I have to walk in the opposite direction. I have to measure minus 2 in the opposite direction, which means I have to measure 2 going down. And so I will end up in precisely the same position as I did when I went to the point 2 minus 2 pi over 3. So indeed, by adding pi to the angle and negating the radius, I will end up at exactly the same point. Another thing to observe here is that the origin, the pole, has infinitely many ways to be represented in polar coordinates, like so. So 0, 0, which is the pole, the origin, is equal to any point of the form 0 theta. So we can have absolutely any theta, but since the radius is 0, we never leave the origin, right? So we have our algorithm which says in order to go to a point, we must measure the angle away from the axis and then walk along the measure distance r along the rotated version of the axis. But since r is 0 here, we're not going to leave the origin. We just rotate our axis by some angle, but since r is 0, we just stay at the origin. So this pair of polar coordinates always represents the origin for any value of the angle theta. And so this algorithm gives you an alternative way to represent points in the plane. Now, instead of using x and y, which are orthogonal projections, which are perpendicular projections of your point onto the axis, you're using another pair of numbers, r and theta, which denote the angle that the direction towards your point forms with the fixed axis, and r, the distance from the origin to your point. So using this pair of numbers, you can equally well represent any point in the plane like so. And so this is an alternative system of coordinates that in many circumstances comes useful and will be even more convenient than the Cartesian coordinates.